Hi, we are Sonia González Telles and María José Chaboya Zamora, and we are going to present the practice refraction law for light. This is the overview of our report, and we are going to begin with the objectives. Our objective is to demonstrate Snell's law for light by analyzing the incident and transmitted rays through different surfaces. The specific goals are to obtain the index of refraction of an acrylic trapezoid and a biconvex lens through different methods.
Now we're going to start with the introduction. First, we're going to define what is light transmission. And this occurs when light travels and passes all the way through a transparent object or material. However, this isn't always what happens, and there's a loss of energy. For example, the light can be reflected off of a material. It can be scattered by particles or molecules into different directions and be absorbed and converted into heat, as can be seen in the first figure. Now, we are going to determine what is refraction. Refraction is when a wave is bent because it is passing through a medium with in different speeds. Refraction of light occurs when light is traveling into two mediums with a different refractive index. The bending or change in direction occurs due to a change of speed. For example, when light passes first through air and into water. Since light travels at a different speed in air than in water, it changes direction. So when light enters a material with a higher refractive index, it leans more towards the normal line. As we can see in the second figure, the normal line is always perpendicular to the interface that is between the two materials or substances. And light that enters by the angle of incidence and then is refracted and changed by the direction of the angle of refraction. They will have the different proportions because of the different indexes of refraction. And the refractive index is what measures how much the ray of light is bent as it passes through one medium to another. And it is defined as the speed of light in vacuum divided by the speed of light in the medium, as can be seen in equation 1, where C is the speed of light in vacuum and V is the speed of light in that medium. We can do by, now we're going to talk about Snell's law, which is also the law of refraction. And it is used to describe the relationship between the refractive index of the different mediums and the propagation of the rays in respect to the normal line. Snell's law states that the ratio of the sines of the angles of incidence and refraction is equivalent to the reciprocal of the ratio of the incidence of refraction, as can be seen in equation 2, and it can also be rewritten as we can see in equation 3.
Now we also are going to talk about lenses because they are refractive devices. They are transparent or semi-transparent devices and have two curved surfaces. There are two different types of lenses. The convex lenses in the second figure is figure A. All the rays that passes through a convex lens, they are going to converge into the focal point. And we also have the concave lens. All the rays that passes through a concave lens are going to diverge. And here, the focal point is going to be the point where if we trace back all the dispersed rays, they are going to merge in this point. The focal length of a lens is the distance between the center of the lens and the focal point. We can relate the focal length, the radius of curvature of the lens, and the index of refraction of the lens through the lens maker's equation given in equation 4. It's important to notice that this equation we can only use it for thin lenses.
Now we're going to see the materials and equipments that were used for this report. A ray box, an acrylic trapezoid convex lens, millimeter paper, an online protractor tool, and online software called Tracker. As we can see in the first experimental setup consists of an acrylic trapezoid that was placed in front of a ray box that emits multiple rays. However, we chose the setup that only contained one ray. And this arrangement was analyzed through an online protractor tool for each image of the setup as the acrylic trapezoid was turning to measure the incident and refractive rate. And in the second experimental setup, we can see that we're using a biconvex lens that was placed in front of a ray box with a 5-ray configuration, and a millimeter sheet was placed underneath it. And we used a software called Tracker that was used instead of the millimeter paper, so we were able to determine with more accuracy the focal length and the focal point.
So we're going to begin the analysis. For the first activity, as Maria Jose said, we use an online protractor and we measure the incident and the transmitted angles, which values are given by the first table. But to employ Snell's law, we needed to measure the sines of these angles, and we measure them. They are presented here in the second table, and to obtain the uncertainty associated to the sines of the angles, we use equation 5. Then, if we rearrange Snell's law, we obtain expression 6 that gives us a relationship between the sine of that says that the sine of the incident angle is equal to the ratio between the index of refraction of the transmitted medium, that it's going to be the acrylic in this case, and the index of refraction of the incident medium, that it's going to be the air in this case, times the sine of the transmitted angle. Now what we did was we plot the sine of the incident angle as a function of the sine of the transmitted angle, and we used a linear approximation because if we analyze the equation 6, it has a really similar form as a linear function that has the form of equation 7, where a is the slope of the line that it's going to produce. And if we relate equation 7 with equation 6, we're going to see that the slope of the line we're going to obtain, it's going to be the ratio between indices of refraction. In this figure, we can see the points obtained, plotted, of the sine of the incident and transmitted angles. And the red line is the linear approximation we obtained. We obtain the slope of this line that is given by A, that is presented here, and the point that intersects the y-axis, that is B, but we're not going to use B in this occasion. So using the slope and considering the value of the index of refraction of air as 1.0003, we could obtain the index of refraction of the acrylic and the associated uncertainty that is given in equation 9. Finally, we compare the result with the index of refraction given by the manufacturer manuals, and we obtain an error of 0.67%.
In the second experiment, as I mentioned in the methodology, we used a calibration tool that is called Tracker to help us create a more accurate measure and not solely rely on the millimeter paper in the background. So we obtained the focal point. We used an average that was taken by the different points because we were unable to identify a location in which all 5 rays intercepted one another. Therefore, we used five locations where most of the rays intercepted one another, and the average was taken among them. We had a focal length that we measured as we can see in equation 11, and the radius of curvature of the lens was obtained in a previous experiment, and as we can be seen, is right there within telling us. However, it is important to notice that we are using an equiconvex lens, so this means that the radius of curvature of both sides are equal. So then now we taking the lens maker equation and we rewrite it for an equiconvex lens in which the radius 1 and radius 2 are equal but have opposite signs. Then using this equation, we cleared for the index of refraction and it gave us equation 12. For this equation, we were able to obtain the experimental index of refraction of the acrylic, which can be seen in equation 13, and with its associated uncertainty, which we did by using error propagation and partial derivatives, as can be seen in equation 14. Finally, we compared these results, as we can see in the table, with the literature contained in the manufacturer's manual, and we calculated the error percentage, which is of 5.4%, which we consider that is very good and it is well accepted within the range.
So for activity 1, we observed that the data obtained was extremely correlated, and we also saw in the graph that the points were not very dispersed. This gave us an acceptable result with minimal variation. We think that the error obtained could be due to human error, but we also believe that maybe if we had used more significant figures for the values of the signs of the angles while doing the analysis, we could have obtained a better result. And in activity 2, we could observe that the experimental value obtained was within the accepted range, but we associate the error to an aberration of the lens. The aberration may have made that the rays did not converge to a perfect point, and this may have gave us the errors.
To conclude, we believe that we successfully demonstrated Snell's law on a flat surface in experiment 1 by analyzing the incident and refracted angles and plotting the sine of the incident angle as a function of the transmitted angle, and therefore determining the index of refraction of acrylic. We obtained an experimental index of refraction compared to the literature with a very good percentage error, and we were also able to determine the index of refraction of the biconvex acrylic lens by correctly applying the lens maker equation, and which only gave us an error percentage of 5.4, which we believe is very good on both of the experiments. So we conclude that this experiment was a success.
That's all. Thank you very much.
Thank you so much.